We have seen that the Kohn-Sham equations represent a set of one-particle equations, which is desirable because we can solve them. We have also seen a variety of approximations for the exchange and correlation potentials that are used today for materials research. The Kohn-Sham equations, however, are, yes, one-particle equations, but these equations are coupled. We have already mentioned that they have to be solved self-consistently. The aim of this section is to look into the solution of the equation with a little more details. Let's have a look at the Kohn-Sham equations. Oh, by the way, I'm talking here about Kohn-Sham, but exactly the same problem, and so solution, applies for the Hartree or Hartree-Fock equations. So what we are going to discuss is quite general, okay? What is the problem then? As you can see, in order to determine the output of the equations, the output is the set of eigenvalues and eigenfunctions, we have to diagonalize a Hamiltonian. Actually, for very big problems, you do not fully diagonalize. As you know, diagonalization is a cubic problem in terms of the scaling of the algorithm. And if we are not interested to all eigenvalues, iterative techniques can be used or conjugate gradients algorithms. The point is, no matter what one uses, we have to know the Hamiltonian. Now, the Hamiltonian, in particular the potential part, contains the external potential, known term, for example, the position of the nuclei, the Hartree potential, that we know how to write in terms of the electron density, and the exchange correlation potential, unknown, that we have to approximate. Let's suppose that we choose an approximation, for instance, LDA, written here in terms of the energy of the homogeneous electron gas. If we can write V Hartree and V exchange correlation, we know the Hamiltonian, and so we can diagonalize it. The problem is that the electron density, that for independent particle system is simply the sum of the square modulus of the wave functions, all occupied levels, is also an output of the problem. It comes from the eigenvectors. And now the density is required as input for the potentials, and so for the Hamiltonian. In order to solve this, we will follow an iterative scheme called the self-consistent field approach. The self-consistent procedure is very often attributed to Douglas Hartree. We used it to solve the Hartree equations. And there is a little doubt that it is thanks to Hartree that we use the procedure today, also for the Kohn-Sham equations, in the way developed by Hartree. It is, however, important to mention that Hartree did not invent the method from scratch. Robert Lindsay, who spent an academic year working with Bohr and Kramers during his PhD at the MIT, introduced a rudimentary self-consistent field approach already for the Bohr's atom theory. He is in fact acknowledged by Hartree in his second paper on the Hartree equations. Okay, back in business. How does this SCF procedure work? The idea is the following. We have an initial guess for the wave function, or equivalently for the density. Let's call it input density. Input because, thanks to this density, we construct our potentials. We haven't started our iteration cycle yet, so let's call this iteration 0. Let's solve the eigenvalue problem. We have as output the eigenvalues, eigenfunctions, and by the eigenfunctions, a new density, the output density. We can at this point compare the newly obtained density with the previous one, the input density. Most probably, it will be different. But if the density has not changed, or to put it in a more operative way, if the density residual is smaller than a certain small value, called tolerance, well, we have finished. We have obtained our converged eigenvalues, the energies, eigenfunctions, and of course, the final density. As I said, this is rarely the case as a first step. So, if the residual is not small, you iterate. You cast your output density into the input density and start again. Construct again the potentials, diagonalize, obtain new wave functions and density, and iterate this procedure up to convergency. When the input density inside the potential generates, by diagonalization, the very same density, it is consistent with itself. It is self-consistent. And the procedure ends. This seems smart and simple enough. However, even if the idea holds, in practice, this procedure does not converge so easily. What happens is that the output density might be very different from the input density, and this big fluctuation of the density do not converge well, or ever. One way to help the procedure is to try not to let the density change so abruptly. For example, you can decide to let the new input density to be not just the output density, but a mix of the old input and output densities. And you can play with the parameters alpha and beta to drive the convergence. You can generalize this procedure, letting the new density remembering not only the previous value, but the density values at all previous steps, of course with certain coefficients. It turns out that these mixing schemes are very helpful in accelerating the convergence of the procedure, and they can be arbitrarily complex and clever. So, this is the main idea of the self-consistent field algorithm. I say main idea because in practice, other technicalities come to play, and depending on the approach, the basis used, the kind of system we want to study, small differences in the procedure can be detected. Before finishing, I'm going to give you an example of these technicalities, due to the fact that we tackle, for instance, a solid with a big primitive cell. To realize what the problem is, let's write the Hartree potential in reciprocal space. Here, G is the reciprocal lattice vector. Now, if we have a big primitive cell, the smallest G vectors will be small. So the potential contains a very small term, it's G squared, at the denominator. This implies that even a small change in the density will produce a very different Hartree potential. And the iterative procedure will have a lot of difficulties in converging, exactly because of this intrinsic divergency, which is proportional to 1 over G squared. These wild fluctuations, because of this divergence, are sometimes called sloshing instabilities. Well, how to cure them? A possibility very often used is to change our mixing by introducing this term here between brackets. What is the difference with respect to the normal mixing? We introduce a constant G0 of the order of the characteristic reciprocal length of the system. What is the effect of this constant? Well, first of all, this term is innocuous for big reciprocal lattice vectors. We end up with the previous mixing scheme. What about small reciprocal lattice vectors? Well, in this case, it turns out to be very important. In fact, it counterbalances the intrinsic divergency contained in the residuals. And so it avoids strong fluctuation in the potentials, with the net effect to accelerate the convergency procedure. So this was only one example of the technical details involved into the SCF procedure. Be aware that the field of research for better self-consistent techniques is still very active and rich, both for the mathematical algorithms and also for the numerical massively parallel implementations. For the purpose of this course, we now have a clearer idea of how the Kohn-Sham solver is implemented in ab initio codes. Goodbye.